Okay, a couple weeks ago at our last meeting, I went over the BuddiStick, which was an antenna that I bought for a particular problem we were trying to solve. What we were wanting to do was come up with a way to have a quick install of an HF antenna for parks on the air activations. And the idea there was that we wanted to be able to move from park to park fairly quickly and try to get as many parks as we could for the radar award. So after looking at a variety of antennas, I selected the BuddiStick. At the last meeting, went over how the BuddiSticks put together and how I tuned it for 40 meters. This video, I'm going to go over the BuddiStick, same BuddiStick, and show how I tuned the antenna for 20 meters using a binary search and an antenna analyzer. Now, the BuddiStick instructions has a way that you can tune with your radio by listening to the signal at various locations on the loading coil. But I thought this would be a little more straightforward and came up with this approach. So the other thing here is that I wanted to make sure that I had a technique that I could easily reproduce the tuning as we change from park to park if necessary. This did it for me. So for this particular tuning on 20 meters, we're targeting 14.288 megahertz. And the reason for that is that's the middle of the general class, a single sideband band on 20 meters. And what I want to be able to do is put the resonant point of the antenna right in the center of that section of the 20-meter band so that our HF transceiver will work at the best SWR possible for this particular application. Judy does most of her work on POTA using 20 meters and 40 meters. So we'll get started. Okay, a little bit of review that we covered at the meeting. Now, this is the BuddiStick package here. And what you have is a nice bag to store everything. It comes with a couple of fixed length antenna elements, a telescoping antenna elements. It comes with a loading coil, and you notice on the loading coil there are blue and black markers indicating the position on the coil. And the way it works are these little connectors here will hook into this wire at whatever point you want to put it, and then you tighten down the plastic nut and jack, and it forms the jack and then secures the connector to the coil at whatever location you're at. The BuddiStick also comes with the radial cable that you can use if you're using it on a, say, a tripod mount or a clamp mount of some sort. And it also has the base here that can be used to attach it to a camera tripod. For this application, rather than using the tripod or anything like that, I selected a 3-magnet mag mount. And we talked about in the last session, the reason for that was with HF being lower frequency than typically than VHF and UHF, you need to have more capacitive RF coupling in the base to the roof of the vehicle, so you get a better ground plane. So that's why I went with the 3 magnets. And for purposes here, I'm using my Rig Expert AA54 antenna analyzer to generate all the data. So just a quick review of the construction of the BuddiStick. This is a table mount where it's clamped onto a picnic table, and you install the two fixed length elements. Then you install the coil, the loading coil, and then on the top is the telescoping antenna element. And then taking a look at the loading coil, you can see there's a jumper here at the bottom, and you can see the black and blue marks that are on the coil, and this is showing a connection for the jumper to this particular coil. And if you wanted to locate it other places in the coil, this connector can be moved pretty easily and secure. So that's kind of the mechanics of the BuddiStick. So what I did in looking at the BuddiStick, you've got a coil here, and the spacing on the blue to black spacing is 5 turns. So here you would have 5 turns, and then here's 5 turns. And what I wanted to do was come up with a little worksheet that I could use to keep track of where I have the connector connected and what the values are. So came up with this. This is tap 1, which would be the very top coil. Tap 2 would be the 5th one down, then the 10th one down, the 15th down. So I designated these major points, the ones that are marked, as taps 1 through 8. You can see we go down to 8, and then at the bottom is the jumper, and that's where the jumper's connected, and I have that designated here. Then within the major taps, I just designated the tap A, B, and C. So say, for example, I end up located here on the coil, I can designate it as tap 3B. And so that's just kind of the structure that I put together to gather the information for the test. And then this column here is just which test number it is. I wanted to keep the sequence, know what sequence I did the adjustments. So the first one would be test 1, the second attempt would be test 2. And then get the approximate resonant frequency at that particular tap setting in megahertz and record it. And you really don't need to be extremely precise with this result. The way I did it is I just ran a pretty broad frequency sweep of where I thought the resonance point was going to be, and then just eyeballed it off the graph on the antenna analyzer. Because what it's doing, it's going to tell you whether the only decision you're going to make from the information is whether you need to shorten or lengthen the antenna. And then I've got a couple, 2 columns of that where I can put, say, the test for tap 1, 2, and 3 are in this column. And then if I go into the finer taps, then I put those results there. Then the top telescopic element, I record what length of that element I end up with. Now, you've got, doing this, you have 2 knobs, I'll call them, that you can turn to adjust the resonant frequency. You can adjust the position on the loading coil, like we just discussed, and you can adjust the total length of this adjustable telescoping element. And one way to look at it is the adjustments here on the tuning coil are kind of coarse adjustments, and then you do your final fine adjustment with the length of the telescoping element. So what I did in a binary search, a binary search works on quickly finding, say, for example, in a column of numbers. If the numbers are sorted from low to high, and you want to find the location of a particular number, the way the binary search works is that your first attempt to find the number is to go to the middle of the array of numbers. So here we're going to do the same thing. First attempt, we're going to hook the jumper right in the center of the binary or the loading coil, and then determine the approximate resonance frequency at that point. So that's what I did. I put the connector right here in the center, recorded at 10.5 megahertz, and that obviously was too low because I'm shooting for that 14.288. So that tells me I need to shorten the antenna to get it up into higher frequency, and I can do that by shortening the loading coil, and I can shorten the loading coil as well by moving the tap up, because what happens is this jumper here takes all of these coils out of the circuit, and you're only left with these. So if I'm here, if I put that jumper here, then the only coils that are in the circuit are these coils. So since I'm too low in frequency, I need to shorten the antenna. That tells me I need to go higher up the coil. So where I go is the next midpoint. I go to tap 2. That's the midpoint. Actually, that's not quite the midpoint. Anyway, it's higher. So I went up to tap 2. And at tap 2, I found that I was at 15.6 megahertz, which was too high. So then I had to go down lower, and then I went to tap 3, and it's 12.3 megahertz. So you know that your sweet spot somewhere in between these two. So after seeing that result, then I went to a finer resolution here on tap B, and it ended up at 14.050 megahertz. So the tap sequence was I started here, then I went to here, then I went to here, then I went to here. So you're just bracketing wherever that sweet spot is to get to where you want to be and find out what that resonant frequency is. So 14.050, I'm in the lower end of the single sideband band, and down in the CW area. So I'm going to have to adjust the telescopic element. And one thing I forgot to mention is that when I started this, I had the telescopic element fully extended because I wanted to get in a position where at some point when I was doing the fine tuning, it was going to require a shortening of the telescopic element. And that's what I had here. We're 14.050. I want the resonant frequency to go up, so that means I'm going to have to shorten the telescoping element a bit. Now, the way I did that is I measured the top section of the telescoping element, and it was 11 inches when it's fully opened. So I went to the midpoint there. I moved the telescoping element to where it was 5.5 inches long. The exposed length of the telescoping element was still off a little bit, and did a final adjustment to 7.5 inches. And when I did that, with the length at 7.5 inches, while I was at that point, I went ahead and measured the SWR at these frequencies to see how well it would be in that section. So here's our target. We've got it SWR at 1.44. It's the minimum SWR I've recorded. So we've met the objective of getting the resonant frequency at or near that midpoint of the 20-meter general band. And you can see even from these numbers that it maintains the SWR in a pretty good number through the whole band that we may operate when we're doing POTA, or I should say when Judy's doing POTA on this antenna. So then as a final check, I went ahead and did a full SWR scan for that section of the band. And you can see we're down here about 1.5 through the most of the operating band. So, you know, we're like from here to here, the SWR is right where we want it. So I put the note on how to tune it as a reminder, because this is a document I'll use if we set the antenna up and say I've changed it. This is how I can get back to this setup. I place the tab at 2B, which I can identify from the table we looked at. Excuse me. And then I adjust the top section to 7.5 inches in length. And then this is just a duplicate of the information I had of the actual SWR reading. So with this one document, I can get back to this setup very easily, you know, if I wanted to change it. So let's say, for example, if you look, as we get towards the CW part of the band, which I don't know, it's probably down in here somewhere, the SWR starts going up, as you would expect. These are, being a loaded coil antenna, the bandwidth is relatively narrow compared to a dipole. So what you would have to do, let's say if you wanted to operate CW on this antenna, you'd have to go through this same procedure, but you would use a different target frequency. Rather than the 14.288, maybe it would be 14.100. And then you go through that binary search process to find that sweet spot and compute the, or just document the where the tap is and what the top adjustment section is. So anxious to see how this works this weekend. The other thing I wanted to put in here is the 40-meter tuning that we went over at the club meeting, where I'm using the BuddiStick 40-meter tuning. This is the tri-magnet mount. And so the way I set it up, the results I had from that tuning was that you take the telescopic element fully extended and shorten it so it's 1 inch sticking out from the end of the second element. Both fixed sections, the fixed elements, are installed below the coil. No taps, you just leave the tap open, and you'll get a SWR plot like this that shows the 40-meter general single sideband frequencies. And you have a little higher SWR here on 40 meters than we ended up with on the 20. But even at that, we're with the portable transceiver that we use, which is a Kenwood TS590SG, we're able to, with the internal antenna tuner, bring this in, and it works very well. The other thing I've done is that after this initial setup, when we first set it up in field to operate, I went ahead and ran the antenna analyzer to confirm that I had that same SWR curve, and we were dead nuts on. So it's repeatable, which is something that you really need to have in a portable installation where you're going to be changing things from time to time. Another thing to consider, let's say, for example, I wanted to move this antenna to another vehicle, you would need to go through the same tuning procedure that I did on this one. And the reason for that is because the vehicle will be different, the ground plane is going to be different, and it'll affect your SWR. So to be certain of where you're at, you go back through this binary search approach and find the sweet spot for whatever your target frequency is. And that's about all I know. If you have any questions, give me an email or a call, and I'd be happy to go over it with you. If you do want to email it something to me, probably the easiest email address would be to use k3sks@arrl.net. So that's it, 73.